So we'll get started, okay?
Okay.
First, I'd like to thank Professor Shuku for the kind introduction and all the organization for this online forum. And I would also like to take this opportunity to thank the TC304 and also Professor Yoshida for inviting me to this online forums and give us an opportunity to share some of our recent progress on this regard. Okay, so the topic of my presentation is actually smart sampling strategy for data-driven site characterizations. And basically, going to have two parts in this presentation today. The first part is going to be benchmarking that KK and Shuku has been talked about. And the method we're going to use is basically the Bayesian complexity sensing, called BCS. So we're going to briefly introduce the method and we're going to give the result of our benchmarking analysis. And the benchmarking will including one set of the data from Shuku, and also we have been conducting the benchmarking several months ago using the real data set. So I will also share that result as well. Okay. And after that, I will try to echo the comment that KK made during his presentation, saying that what is the merit and the added value. And I totally agree. And this is the key point. And if we really aim for the engineer practice to use our method, we must be able to clearly demonstrate the added value from this data-driven site characterization. And we try to do something on the smart sampling side. And today I'll go to give you an illustration of how can we use this data-driven strategy for CPT-based liquefaction assessment. Okay, and finally I'll have some concluding remarks. Okay, so let me first start it with the talk about the benchmarking and talk about the method we use, which is the Bayesian complexity sensing. So let me start it with the complexity sensing first. Okay, so basically what is complexity sensing or complexity sampling? And this is really the so-called new starting problem in 2005 and coming up from the signal image processing field, and now has been very popular in this kind of digital image field. For example, almost all the digital CT, MRI now, they're all using this kind of thing. And a lot of this kind of online image transaction, for example, JPEG file, a lot of file also using this kind of thing. And basically the idea is that, for example, you have a high resolution image, for example, a 1 million pixel image on the left-hand side. You actually don't need to measure that at all or transmit at all. Using the method, you only need to, for example, about 9% of the data has been measured, and you're able to represent the image and transmit the image in a very efficient way. Okay, and the basic idea of this kind of thing, it allowed me to use a 1D data as illustration. So basically, we have, for example, this is a CPT data. Then you have some kind of scatter in here and there. And the complexity sensing basically saying that the data, you will say it as F right here. And F is going to be a weighted summation or a limit number of base function. And the B or BI here actually represent the base function. And the omega I or omega here is represent the corresponding weight. Okay, and you're using the base function as, for example, a cosine function. And this is almost identical to the well-known the Fourier series expansions. Okay, if we remember from our probably undergraduate mathematics, we know that any functions can be well represented by a Fourier series expansion, and basically with different frequency. So you can see the cosine function here and the amplitude here. So basically, you can treat that the B here, the BI here represent to the cosine function with different order of magnitude, different frequency, and the omega I here is actually their corresponding amplitude. And graphically, it's basically saying that you can treat this CPT data as a summations of from low frequency, so it's a constant line, linear increase to a high frequency, and with a corresponding weight omega I, that kind of things. And even the good news is that quite often people found that for many signal, including a lot of geotechnical data, then the most of the omega I is basically that zero. So that means you actually do not need a large numbers of base function if you want to represent the data here properly. Okay. So let me give you an illustration in the next slide. So say this figure. So if you starting out with the first base, and then you do this add the second base function with a different frequency, another one, another one, another one. You can see that as the number of the base function increase, then the red line here is actually gradually converged to the original profile. And the good news is that you don't need a large number. You probably only less than 20. In this case, you're able to approximate the original data very well. So this is actually provide a very attractive idea how to reconstruct or recover the original profile from a limited number of measurements. By saying that if we have, for example, 20 data points along this QC measurement, maybe we're able to identify these 20 important base and their corresponding weight. In that way, we're actually able to approximate this original function already. So this is basically the idea of complex sensing. Okay, and the mathematical framework is basically the F is the signal we're interested in or the CP data we have, and basically the prescribed base function and the corresponding weight. And there's two things to be noted. The first one is the base function here is actually independent of the data you have. For example, cosine function, or you can use the Wheatley function or that kind of thing. And the second important point is the magnitude of the lot of element in the omega I here is actually equal to 0. So you only need to identify the important one. So this is make it possible that we have a limited measurement. That's what I call sparse measurement. You define it as a vector of y, then you can easily recover the original profile. Okay, so how can we make it happen? So basically y is just part of the original figure. So the phi here is basically a matrix reflecting the projection of the measurement. Okay, so basically if an original signal f, you take some kind of measurement, so it's the measurement matrix here reflecting the measurement projection, and you put the f equal to b omega here, and that you rewrite it, the phi and the b together, that established a relation between the measurement and the vector omega. Okay, so this is actually how you can, from your measurement, you allow you to estimate the omega here, because the phi and the b, they're actually independent of the problem that we have right here. Okay. So there's different way that you can actually solve this problem, and there's some of them are non-probabilistic, some of them are probabilistic based. Okay, for example, one of the popular algorithm is so-called orthogonal matching pursuit, OMP, or we can use the Bayesian method. And the Bayesian method is always attractive because when the measurement data is very limited, that can give you an uncertainty quantification as well. Okay, and after you have the approximations of the weight vector, we call it as V cap, and then you can just set those 0 to the trivial location. So we just find that those that are important, they are not 0, we estimate that, and for the rest, you must basically set it to 0. Okay, so and after you have this omega cap, you basically just put it back because the B is p-squared, so you can actually estimate your original signal in this way. Okay. So this is the basic idea. And if you are interested in uncertainty, you can always put a Bayesian versions on that. And this is what I call Bayesian complex sensing or complex sampling, or we sometimes also call it as Bayesian supervised learning. It depends on which field you are. The mathematics is basically identical, but in the machine learning, people tend to call it as Bayesian supervised learning. But in the image processing, they tend to call it as complex sensing. But the basic idea is just to estimate the posterior distribution of omega cap given your measurement y here. And this is just a Bayesian theorem. And we can either derive it analytically, because the limit of time, I'm not going into detail, I just directly give the result. So we can actually analytically derive the equation. So they give you the mean vector of the omega, or even the covariant matrix of the omega as well. Okay. Or nowadays, you can alternatively using Markov chain Monte Carlo simulation, for example, gig sampling. So basically, this is a typical application of Bayesian, and then you couple it with the MCMC, and that can generate a huge number of samples of the omega cat directly. And from the omega cat sample, then you can put it back. Basically, just B times omega cat, they give you the original signal. And you can give you the mean, you can give you the covariant, and give you everything. Okay, so this is a basic mathematics. As I mentioned, I'm not intending to go into the detail because today is really for the benchmarking. Okay, so although the illustration is for 1D, how about the 2D or 3D? Because the real problem is always 2D or 3D, right? And the good news is that the BCS is directly scalable to 2D and 3D because the idea is very simple. The base function, you just change from 1D to 2D. And the base function is prescribed. It's actually not involved in the calculation. Our calculation is trying to estimate omega t, right? So that's why BCS or CS is directly scaled from 1D to 2D to 3D because the whole process of estimating is really the omega. It doesn't matter whether it's 2D or 3D because 1D, because that is actually specified by the base functions. And the base function is prescribed and is done independently out of the problem of the calculations. Okay, so you can do similar to a 3D, basically just the base now is just 3D, and we are going to estimate omega t here rather than tackling the base functions. Okay. So with that, I will quickly show about some of the benchmarking exercise we have been doing. And Shuku has given a numbers of exercise, but I only did once. Okay, so this is I think it's the virtual ground number 2, if I remember correctly. And this I only use the training data set number 3. So here, so basically using 3 CPT, trying to recover the whole size. And the difference is that we are actually able to recover the whole site at once, because when we estimate the omega and reconstruct the data, because the base function is 3-dimensional. So we actually reconstruct the 3-dimensional random field sample directly. But we're going to pick the location of the blue color here as 12 CPT for validations. Okay. So this is basically the result we're going to do. And in this exercise, we're actually using MCMC. Okay, we're using the Bayesian CS together with the MCMC. Okay, so this is the result that we get so far. Okay, so for 200 random field sample, so basically we generate 200 this kind of 3-dimensional random field sample, and each random field sample have 40,000 elements. Okay, and this gives you a mean profile, so you can see that's very clear. There's 3 layers. And the shallow layer, that the soil is pretty strong. The mean value of the QT is bigger. And then you have the second layer, that is the soil is pretty weak. Okay, you can see the blue color indicates it's a low QT value. And then after that, there's another layer of soil is a little bit stronger than the second layer. Okay, and also the layer structure is very clear. Along the horizontal direction, there basically is a layer structure. They have some kinds of inclination, and there's some kinds of stronger soil in this corner as well. And we can take a cross section, we cut it, you can see what the inside in there. Okay, and the advantage of the Bayesian version of the complexity sensing is that it not only gives you the mean or the so-called best estimate, it also gives you the uncertainty or give you the standard deviations. So here I directly plot the standard deviation for all the 3D element that we have. We can see that more or less the standard deviation is within about one the QT value or 1 MPa, that kind of things. Okay, so you can see that in the middle, somehow different location that have some variation of the standard deviation value as well. Okay, and we can do the same thing for the IC value. Okay, so this is the IC value. Again, very clear, it's a layer structure, have a little bit of inclination as well. So you can see that here, the thickness here is the second layer, the thickness here is a little bit larger than the thickness in here. Okay, so you cut it, probably see a little bit better, and also can show the standard deviation as well. Okay, so this is somehow the standard deviations of the IC value that we produce. And keep that in mind, all this kind of thing that will be coming up from 3-dimensional random field sample directly, because we are using MCMC in this case. Okay. And this is give you a detailed comparisons with the 12 selected location for the CPT measurements. And because we're using random field sample, so we can get both the so-called the mean estimate. So this is the red color. The red color here is really the the red color here is really the mean value, and the blue dashed line that we are talking about here is the confidence interval. Okay, so you can see that overall the trend. Okay, and they in the middle, they tend to get it better, and then there's a sudden change. They basically the result predict is a more gradual change and that kind of things. So overall, they can pick the 3 layer, the first layer, second layer, and the third layer. They also can do that. And in terms of SBT, the soil behavior type, because it's based on Robertson chart, and this is the problem that actually has been mentioned by KK at the beginning, that, for example, it's really hard to say, for example, here, whether this is really a layer or it's really just an uncertainty that's due to the Robertson chart, because Robertson chart itself has uncertainty. So in engineer application, whether this going to treat it as another layer, or whether it's going to treat it as it's just an artifact from the classification system. So my opinion is that if you're really interested in this kind of soil stratification problem, probably it's better that we're using the borehole data, because the borehole data, you actually have a visual inspection, and the people see the soil or rock sample, and that has less uncertainty involved, because the CPT always involve this kinds of Robertson chart uncertainty, and how applicable to Robertson chart to different the soil in different part of the world and that kind of things. Okay, so this is and using the parameter that has been defined by KK and Shuku, RNSE, and the identification rate AR, we actually come up with this performance summary. Okay, so we are doing ground G2, and the training data set is T3. Okay, so the average is about 1.7, and the best is about 1, and the worst is Q is about 3. And this is really use the method that I think is being used by Shuku, because he actually compared the 12, right? So for the 12 CPT data as validation, for each one of them, I think the RNSE was calculated separately. And this is really the average of these 12 RNSE. And this is the best of these 12 and the worst of these 12. And similarly, for the identification rate, I think the average rate is about 76%, and the best rate is 85, the worst case is 63. Okay, and again, this is following the method has been used by the Shuku. So among these 12 CPT for validations, okay, the best one is 85% is correct. On average, 76. The worst case, about 63%. Okay, and the computer set we use is the student use just a normal laptop, desktop computer. And the execution time, we are very fast. Okay, Shuku mentioned that talk about 10 hours or something like that. We only need 4 seconds for 200 random field sample. And this is for MCMC to run probably about 5,000 to 10,000 MCMC step, because and then we pick 200 independent sample from that MCMC queues. And this time also including the so-called training time and the prediction time, because for us, we don't separate that. We just use that 7 or 6 CPT, I don't remember, as input. We throw into the software that we have, and then that's directly the 200 random field sample that's generated, and we do the statistic based on that. Okay, and the time is actually almost instantaneous. Okay, we hit it in almost real time, we get the feedback. So we don't, so far we are not suffer from the computational yet for these problems. Okay, and this is slide showing the similar information, but we're doing a slightly different way, because we are actually doing the random field sample, right? So each random field sample, we are able to calculate a RNSE. Okay, by treating the 12 CPT data as one set of the data at the same time. Okay, so we tried it at the single data set for this 12 CPT. And because we now have 200 random field sample, we can generate 200 RNSE for 12 CPT together, and that's give you an overall performance of the variation between different random field samples. Okay, so the average is the 1.85, and the standard deviation is pretty small. And similarly for the IC and the average of the identification rate, and it's very stable. Okay, so that means among different random field sample that will generate, actually the in terms of the performance they're actually pretty stable. Okay. Okay, so that's pretty much what I'm going to talk about for the benchmarking for the simulated data. But I also want to share that the benchmarking was been done about early this year, several months ago. We're using a real data set. Okay, and this data set is actually taken from the TC304 data set, and this is actually TC304 DB, and it's the data provided by Professor Mark Jackson from Australia. So we just pick a section of the CPT database he have, and we enlarge here. Okay, so that actually this area including 50 CPT, all real data. Okay, so basically what we do is what we did is actually very similar to what is Shuku has been talked about today. So we pick up this area, we are about 30 meter by 20 meter and 5 meter in depth. And we divide it by 1 meter by 1 meter by 0.55 centimeter. And the element degree of freedom that we have is actually 60,000. So the sample that have been created by Shuku is 40,000, but here we actually talk about 60,000. And the dimension is very similar, okay? In the depth is actually reduced by half, but the element, the interval between the cell is actually also decreased by half. So the number of data point along the depth direction is actually identical, okay? So with that, we are trying to say that we actually run quite a number of random simulation to pick randomly, but I don't have the time to go into all the detail, but so just quickly. So here we just pick, for example, 20, and we're going to recover all, and we compare the remaining 30. Okay, so basically we select 20 to recover the whole three-dimensional. And then at the remaining 30, we actually have the measurement data, allow us to do a direct comparison. Okay, so this is the result that you can see. So this is the real data. And the real data, the field is actually here. The field is not just a stratification. That's why I'm trying to emphasize. The soil in geotechnical engineering, we always simplify the soil as a layer. But the real ground probably is just something like that. You have a zone in here. So this is a zone of blue color, indicates a weak zone. And this is a zone of the, actually we red color, that's the soil is actually much stronger. And you cut it, you can see there's one zone. And this is, if you think about it, you really look at a lot of geophysics data, the geological cross-section and geophysics method, they quite often will give you something like that. And this is very similar from our interpretation result. And similarly, we can produce the standard deviation to indicate uncertainty as well, okay? In terms of each comparison with different 30 CPT, you can compare that. And again, we got the mean prediction, we got the 95% confidence interval, and the rest, the red solid line is the real data. So we actually, the overall, they can catch majority of the trend, and take that in note, some of the data is missing. And our method is okay. We don't need to actually, each one have to equal length and equal that kind of things. Okay. Okay, so this is a quick summary. And then again, the average is about 1 point something, and the best is a 0.4, the worst is 2.4. And the executing time is about 1 minute. Okay, so this is a typical result that we've been getting. So it's actually, we are running this kind of three-dimensional, talk about 60,000 or that kind of magnitudes of unnumbered element. Now we're able to do it within about 1 minute, okay? And the one that produced by Shuku is because it's highly simplified, because the layer structure is too obvious. So for us, it's actually faster, okay? And this is the one that, again, because we're Monte Carlo samples, so we're testing that the difference between each one of the 200 random field sample. So you can see that actually they're pretty stable. Okay. And so this is pretty much for the benchmarking, and with that, I probably want to make a few comments on that. Okay, so first one, the BCS is actually a data-driven method. It's a non-parametric. So you can see for the all formulation, we do not assume what kinds of marginal distribution. We do not assume whether it's a trend function, it's a linear trend function, or what kinds of autocorrelation function, exponential or whatever. No, we don't assume that. We actually, the only thing that we need to specify is just what is the basic function you're going to use. Whether you're going to use a DCT, a discrete cosine function, or you're going to use a wavelet, what kind of wavelet you're going to use, okay? And it's actually directly applicable to non-stationary or non-Gaussian data, because that is quite often the real data will involve multiple layers. And some part of for the soil, part of the soil maybe have the large variability, and part of the soil may have small variability, and then quite often they're non-stationary. And that is actually create a lot of problem for many geostatistical methods. But luckily, the BCS is able to get away from that because it's non-parametric. We never rely on any assumption on that. Okay. And the method is very effective in terms of if you have sparse data. And also it's highly computational efficiency is very high. It's typically now it's within minutes for three-dimensional case. Because the method itself is it's directly scalable. So from 1D to 2D to 3D, mathematically is basically the same, right? And one of the attracting or better appealing features of the method is actually they provide both the mean interpolation result and as well as the quantitative uncertainty assessments This is what we call the BCS variance or the standard deviation. And this is actually have a lot of benefit that we should further leverage on. Okay, and the BCS is very similar to the quicking. I know that some people use quicking, and the quicking is basically a parametric method. And they have to assume the trend function, assume what kinds of semi-variable ground function, that kind of thing. And it works very well when you have a large amount of data. Okay, but when the data is sparse, you have a very limited number of data, then you don't have the solid ground to establish the trend function type, the autocorrelation function type, then you get into trouble. And BCS actually filling that gap very well. That gap is critical for engine application because quite often we have limited data. Okay, so this is and the second part of the presentation today, I would like to share some of the, I believe that the merit and the added value for this kind of data-driven methods, okay? And one of the particular points I would like to highlight is the BCS variance, the standard deviation, is actually offer the insights that into how good your predictions. And if you have additional resource, if you want to improve your prediction, and where should your additional measurement, for example, borehole or CPT, should be added. And this is what I call smart sampling and smart sensing. And I'm going to illustrate that through example of CPT-based liquefaction assessments. Okay, and this is one of the classical photo taken in Japan showing that the liquefaction induced damage. You can see the reinforced concrete structure here. They are actually sinking into the ground and tilting. And the structure is still have full integrity, but the building has been damaged because the foundation failed. Okay, and this is actually a consequence of the liquefaction. And under the ground, the spatial distribution of the subsurface liquefaction zone, the soil zone, actually greatly affect this kind of damage because the differential settlement, how it tilts and that kind of thing. Okay, so it's very important to somehow able to eliminate or predict where the spatial distribution of these subsurface liquefaction soil zones. Okay, and quite often CPT, because they provide a continuous data, and it's very popular in the earthquake engineering. And the method is pretty simple. You are using a cyclic resistance ratio, we call it CRR, and using CRI is actually directly calculated from the CPT measurement, QC and FS, together with the earthquake magnitude. And this is going to treat it as a resistance of the liquefaction. At the same time, you're going to bring in the so-called cyclic stress ratio, CSR. It's calculated based on A maximum, is peak ground velocity. And this is actually treated as some kinds of loading. And the factor of safety against liquefaction is Fs equal to CR divided by CSR. Okay, but as most of the geotechnical methods and this kind of calculation only can be done at the location with the CPT. Okay, so for the location without the CPT, cannot use. So quite often in the old time, it's actually you try to add more points, CPT data point, or you try to assume that between the CPT, they're going to be equal to each other or homogeneous. Okay, and now using this kind of data-driven method, then BCS can be used to estimate the factor of safety at locations without the CPT measurement from the sparse CPT measurement data in a data-driven manner. And more importantly, the CPT not only give you the so-called mean estimate, but also they provide this variant in terms of uncertainty and can be used to check whether you believe that your result in terms of factor of safety is good enough, or you are confident enough, or you think that you should add more data or add more measurement, and exactly at which location that you should put your additional CPT in a tactic manner. Okay, so that's what we are proposing right now, so-called smart sampling. So basically, if you want to do the CPT-based liquefaction assessment, you should try into a tactic manner. So at the first step, your preliminary step, you basically add a small number of CPT, and then based on the result you get, you do the BCS interpolation, and you find out whether you should do more data, more tests or not. And the BCS result will tell you how confident about your result. And if you don't think the result is confident enough, you should add more CPT data, and we'll give you the location that where should you add it. Okay, so I'll give you the illustration, and this is using the real data from New Zealand, and that has been suffered from in the Christchurch in New Zealand has been suffered from a series of earthquake for the last 10 years or so. So that's why they have a lot of CPT data in the database. Is open access. So assume that we're going to do a smart sampling. So there's 5 data points. This triangle represent the CPT data point. And we consider there's an earthquake with a magnitude of 6.2 and a peak of ground acceleration of 0.21. And the site actually, the first 5 to 6 meter is a liquefiable clean soil. So we're going to evaluate the liquefaction hazard based on the CPT data. And the next slide is basically showing the CPT data that we attended from the database. So they're real data. So using the equation that I've been showing you the previous slide, you're able to calculate the factor of safety at each location of CPT. But the problem is that now you only have the factor of safety at the 5 locations. How about the distance between each of them? And this is a BCS can come into make a contribution here. You can use to generate a factor of safety cross section with high spatial resolution. Okay, so this is give you the result. Okay, so can you see the result right here? So this slide is a bit bigger and tend to be slow. So on the top, you can see this is the mean factor of safety. So we original measure data, we only have along the 5 CPT data, but now we're using the BCS, we can actually create a cross section with high spatial resolutions. Okay, and in the second plot here is not only that we're giving the mean value, in the second plot here, we're actually giving a standard deviation of factor of safety. Okay, so you will know that which part you have confidence. For example, this red and blue color here, so that typical means that the standard value is about 0.5. For factor of safety here is about 1, then a standard deviation of 0.5. That typical indicates not very reliable. So probably we want to do more CPT measurement. And you want to do more CPT measurement, which location should we put? So in the last plot in the bottom here is basically we'll do a summary along the depth, along the vertical direction to calculate what is the summation of the standard deviation along the depth. So you can see that at the coordinate of 1, 1, 2, this is have the maximum summation of standard deviation. So that means that if we put a CPT right in here at 112, then probably will get the most information in terms of improving the prediction of the factor of safety. So that's how we did. We're actually able to find another CPT, real CPT value from the database. And you can see that this is we put the CPT value, we do the calculation again, and that's how you see immediately the standard deviation of factor of safety reduced. Okay, but if I go back and compare with the previous result, you can see that this one actually changed. Not only the standard deviation value, but also the mean value also changed. Okay, and you still believe that the confidence level is not enough, we can add another CPT value. So this is a location of 158. So this will be somewhere in here. Okay, so again, that's the results that you get. Okay, so that's how the things we can do it in a iterative or in an adaptive manner. So that's what we call smart sampling. Okay. So with that, I probably run a little over time, so I will quickly wrap it up. Okay, so basically in summary, the BCS basically provides both the mean interpolation and quantitative uncertainty assessments. You can call it a BCS variance or standard deviation, and you can directly from sparse measurement in a data-driven and computational efficient manner. We typically talk about 3-dimensional within minutes, and some of the fast is actually within a few seconds. Okay, and the BCS, we have been working on this topic for about 7 years or 8 years, and we've been testing the method for quite a number of different kinds of simulated data and real data and that kind of thing. And you have some real data, and then you want to test and you want to put in the application, you are welcome to actually contact me or happy to try out our methods. Okay, and just as just an echo to what KK has mentioned at the beginning of his presentation, then what is the added value? If you really want to attract the practitioner in the engineering practice to use that, then we need to really highlight and demonstrate what is the added value or the value or the merits from our approach. Okay, so this is, I believe that the data-driven method have a lot to offer, but we need to create some concrete example, okay, to demonstrate that something that are variable, but they cannot be achieved in the existing method. Now we're using the data-driven method that we actually can achieve that quite convincingly. Okay, and some reference, if you are interested in the technical detail, because I run it very fast, you're welcome to take a look at the paper when being published. And you can look at my webpage as well, or you get any information you need, you're welcome to send me an email. Happy to have discussions on the following. Okay, and last slide, I would like to acknowledge the funding from Hong Kong government and also the hard work and dedicated work by the students. And Borju is the one that actually run the benchmarking exercise, both the data from Shuku and also the simulated the real data that we have for several months ago. Guangzheng is actually working on the smart sampling, and Hui and Teng Yan, they already graduated, but they're the ones that actually working on the method, and particularly Hui has been working on the software and helping out with wrap up the whole method in a more robust manner. Okay, so with that, I would like to thank you for your attention, and if you have any questions, I'm happy to take that if I allow, because I know that I probably overrun, right?